Well, hello and welcome back to Calculus after a couple days off. We are about to start a new unit, Unit 6, an Introduction to Integration. In the beginning of the year, I mentioned that there would be 4 things that we talk about all year: limits, derivatives, antiderivatives, and definite integrals. With this unit, an Introduction to Integration, we're going to start talking about that third and fourth thing that I mentioned, the antiderivatives and the definite integrals. Throughout this unit, there are 2 major ideas we're going to be looking at. And these ideas are going to seem unrelated, and really, as far as this unit's concerned, they will be unrelated. In the next unit, we're going to look at an important connection between the 2. So important, it's called the fundamental theorem of calculus that will relate these ideas. The first idea is the idea of what's called an indefinite integral, or called an antiderivative. The first idea is called an indefinite integral or an antiderivative. Antiderivative, opposite of a derivative. What this is going to be about, if I give you a derivative, you're going to figure out what it came from. Given a derivative, find what it came from. An indefinite integral or an antiderivative is a derivative in reverse. I give you a derivative, you tell me what had that as its derivative. The second idea, and after this I'll make the video pause for a moment, the second idea we're going to look at is the idea of what's called a definite integral. And the idea here, given a function, we're going to find the area between the function and the x-axis. Given a function, find the area between the function and the x-axis. Given a function, find the area between the function and the x-axis. So for example, if we have, I don't know, maybe a parabola like this, definite integrals will find that area, the area between the function and the x-axis. And obviously there's a little bit more to the definition, but we'll get there when we get there. Take a moment and make sure all this stuff is copied down. So today's video, and the video you're going to watch next week, will be about antiderivatives, indefinite integrals. The rest of this unit will focus on the idea of a definite integral. Given a function, find the area between the function and the x-axis. So in your book, this matches up with section 4.1. And again, this is about antiderivatives. Antiderivatives. First example. If f prime of x equals 4, what is one possible f of x? If I'm telling you the derivative of some function is 4, what's one possible f of x? Well, can you give me a function whose derivative is 4? I'm guessing you probably said something like 4x, because the derivative of 4x is 4. Could you give me another function whose derivative is 4? Not totally sure what you said when you gave me that answer, but maybe something like 4x plus 3? Or maybe you said something like f of x equals 4x minus 200? I don't know. Maybe you didn't pick that one. In general, though, what we can do is we can say that our solution is f of x equals 4x plus c, plus some sort of constant. Why? Well, we know the derivative of 4x is 4. The derivative of a constant is 0. So if you have any function in the form 4x plus a constant, your derivative is going to be 4. Next, if f of x equals x squared, its antiderivative is, if f of x equals x squared, its antiderivative is, before we actually solve the problem, there's a little bit of notation that I need to go through with you. If we have some function f of x, we know that its derivative is f prime of x. We know that its derivative is f double prime of x, and all that. If we have f prime, its antiderivative is f of x. If we have f double prime, its antiderivative is f prime of x. If we have f of x, the symbol for its antiderivative is a capital F of x. So, the antiderivative of f of x equals x squared is capital F of x equals, can you think for a moment and come up with a function whose derivative is going to be x squared? If you couldn't come up with this, don't worry too much. I'm going to give you a power rule in a little bit. But I think our function is going to be 1/3 x cubed plus a constant. Because I know the derivative of 1/3 x cubed is 1/3 times 3x squared. 1/3 times 3x squared, that's just x squared. The derivative of a constant is just 0. Yep, this is going to be my antiderivative of f of x equals x squared. Let me give you a definition, and let me give you some notation for this stuff. I think I'm going to go on the back. Definition. Given a function, f of x, lowercase f of x, we say that its antiderivative is capital F of x if, how do I know that some random function is the antiderivative of this? Well, if I take the derivative of that random function and I get f of x. Given a function f of x, we say its antiderivative is capital F of x. How do I know that some random capital F of x is correct? If the derivative of this thing equals that original function that I gave you. Our notation. Our symbol for an antiderivative, also sometimes called an integral, is an elongated S that looks like this. Why S? It stands for sum, S-U-M. What does that have anything to do with? Not yet. I'll answer that question in a couple sections. If I want to say find the antiderivative of little f of x, I would write it like this, the integral of f of x. Now, after the f of x, there's always going to be a dx. Why? Because integrals use Leibniz's notation rather than Newton's notation. It's saying what has a derivative of f of x dx? That's kind of where the dx is coming from. That thing at the end is the differential, which also tells us that x is our independent variable. Tells us that x is our independent variable this thing over here is the function we're finding the antiderivative of. The function we're finding the antiderivative of. And the answer to this problem is going to be capital F of x plus c. And we call that c our constant of integration. I realize that this might seem a little bit like a mess at the moment. I'm going to make the video pause so you can get all this copied down. Then basically the rest of today will be examples of using this notation, some integration rules, and all that stuff. Take a moment, get this copied down. Okay, to get a little bit used to this notation, if I ask you for the antiderivative or the integral of 4 dx, this is like asking you what has a derivative in Leibniz's notation of 4 dx. We already basically did this problem. The integral of 4 dx is 4x plus a constant. We already did an integral previously, we just didn't write it out with this notation. If I ask you for the integral of the cosine of x dx, it's like I'm asking you what has the cosine of x dx as its derivative. I think you can figure that out. What has cosine x dx as its derivative? I hope you said sine x, but I also hope you said plus a constant at the end. The integral of cosine x dx is sine x plus a constant. Let me give you a couple rules of integration. Rules of integration. If we integrate a constant k dx, this is kind of like what I was doing here. I was integrating the constant 4 dx. What was my answer? It was 4x plus a constant. So over here, what's that integral going to be? Should be kx plus a constant. Two different constants, one that was in the problem originally, one that comes from integrating. Next rule, we have a constant multiplier rule that says if I want to do the integral of some constant k times some function f of x, I can move that k out front and make this k times the integral of f of x dx. This is our constant multiplier rule. We also have a sum and difference rule. This is the integral of f of x plus or minus g of x dx is just going to equal the integral of f of x dx plus or minus the integral of g of x dx. If we have a sum or difference inside an integral, we can split this into two different integrals. Take a moment, get these rules copied down. Then there's an important one, the power rule. Power rule says, if I want to do the integral of x raised to the n dx, well, maybe before I just tell you this, let me show you a few. We already did the integral of x squared dx, and we got 1/3 x cubed plus a constant. Why? Because if I do the derivative of x cubed, I get 3x squared. Multiply it by 1/3, you get x squared. If I have the integral of, I don't know, x to the 4th dx, I'm going to have an x to the 5th, What am I going to have out front? So the derivative of this just has a 1 for its constant. I think 1/5, because if you do 1/5 times 5, x to the 4th, you just get x to the 4th. In general, my power rule says I'm going to do 1 over n plus 1 times x to the n plus 1 plus the constant, or x to the n plus 1 over n plus 1 plus c. I'm going to add 1 to my power, and I'm going to divide by whatever my new power ends up being. Take a moment, get that copy down, and then we'll see how to use it. Okay, I need another sheet of paper. Let's see how to use this now. If we're going to do the integral of x to the 6th dx, our power rule says all we have to do is add 1 to the power and divide by the new power. I can make this x to the 7th over 7 plus a constant. If you don't believe this, this is 1/7 times x to the 7th plus c. What's the derivative of this? It's 1/7 times 7x to the 6th. Yep, that's x to the 6th. If we have something like this, the integral of 2x to the 5th dx. Our constant multiplier rule says we can take that 2 and move it out front. So I can make this 2 times the integral of x to the 5th dx. How about you see what you can do here? Take a moment, see if you can figure this out. Okay, so I'm going to get 2 times, let's see, the integral of x to the 5th is x to the 6th over 6th plus a constant. I'm going to go and I'm going to distribute my 2. That's going to give me 2x to the 6th over 6th. That's just 1/3 x to the 6th plus 2 times the constant. But here's the deal. What is 2 times a constant? It's still just a constant. It's a different constant, but I don't really care about that. I'm not going to have to keep track for right now of what exactly I'm doing to my constant. So rather than this, how about we just say our answer is 1/3 x to the 6th plus some constant. And in general, no, I'm not going to have to do this 2 times this thing and make sure I distribute the 2 to both of those, because again, 2 times a constant, still just a constant. A different constant, but still just a constant. Let's see what we can do with the integral of x squared plus 7x minus 2 dx. We're going to go and we're going to use our sum and difference rule, which says we're going to do the integral of this, we're going to do the integral of this, we're going to do the integral of that. And when we're done, we'll stick a plus c at the end. Take a moment and see what you can do. Okay, so the integral of x squared is x to the 3rd over 3 plus 7 times the integral of x, well, that's x to the 1st. I'm going to get x squared over 2. I'll clean it up in a moment. The integral of minus 2, what's the integral of a constant? Well, it's that constant times x, and then there's a c at the end. My final answer to this problem is going to be x cubed over 3, or 1/3 x cubed, either way will work, plus 7x squared over 2 minus 2x plus a constant. Next, I've got some trig rules for you that will all come from using what we know about derivatives. The integral of the cosine of x dx is like me asking you what has cosine x dx as its derivative. And what would you say? What's the integral of the cosine of x? I hope you said sine x, and I also hope you added a plus c at the end. Integral of cosine x dx, sine x plus a constant. What about the integral of sine x dx? What has sine x as its derivative? Well, I'm not going to say the cosine of x because I know the derivative of the cosine of x is negative sine x. But I think if I have negative cosine x plus a constant, then things are going to work, because the derivative of negative cosine x is negative sine x. Yeah, that's sine x. How about this one? The integral of the secant squared of x dx. What has a derivative of secant squared x dx? I hope you're thinking tan x plus a constant. Going along with that, the integral of the cosecant squared of x dx is what? Well, I know it's going to have to be negative cotangent x plus c, because the derivative of cotangent x is negative cosecant squared x, so negative cosecant squared x will give me cosecant squared x dx. The integral of the secant of x times the tangent of x is the secant of x plus a constant. The integral of the cosecant of x times the cotangent of x is the negative cosecant of x plus a constant. Yes, we will have to know all these rules. The integral of the tangent of x dx. What has tangent as its derivative? Something we don't know yet. We're just going to say not yet. What's the integral of cotangent x dx? Not yet. Take a moment, get those all copied down. Okay, so I think it's time for us to start trying some integrals now. Let's start with this one, the integral of 7x to the 6th plus 2x minus the sine of x dx. See what you can do. Okay, so this is 7x to the 7th divided by 7, add 1 to the power, divide by the new power, plus 2x, that was x to the first, I'm going to add 1 to the power, 2, divide by the new power, 2, minus the integral of sine x is negative cosine x, so I'm going to say minus negative cosine x plus a constant. And I can simplify this to x to the 7th plus x squared plus cosine x plus c. And there we go. Next, let's say we want to do the integral of 1 over x squared dx. Any idea how we can rewrite this problem so we can use our power rule? Basically the same tricks as our derivatives. I can rewrite this as the integral of x to the negative 2 dx. Well then, I'm going to get, let's see, add 1 to the power, divide by the new power. I'm going to get x to the negative 1 divided by negative 1 plus a constant. I do want to get rid of negative exponents, so I'm going to rewrite this as negative 1 over x plus a constant c. If you have a variable with a power in the denominator, we're going to rewrite it with a negative exponent and then use our power rule. The integral of 2 over x to the 5th dx. See what you can do with this one. Moving my constant out front, and I'm going to turn this into the integral of x to the negative 5 dx. This gives me 2 times, okay, add 1 to the power, negative 4, divide by the new power, negative 4, plus a constant. Let's see, this thing is going to be like a negative 1/2. The x to the fourth, I'm going to move to the bottom and make this negative 1 over 2x to the fourth, plus a constant, and I think we should get that. You know what, before we move on, I think I messed something up that we need to go back and correct. Can you go back to in your notes where I gave you the power rule? Our power rule says to integrate x to the n, we add 1 to the power, we divide by the new power. However, there is one power this isn't going to work for. Any idea what power this won't work for? I'm not going to be able to use this power rule if my power is negative 1, so integrating 1 over x. Because if you add 1 to the power, you get negative 1 plus 1, that's 0, x to the 0, that's totally good. But then you'd be dividing by 1 over 0, that's going to be an issue. This power rule only works if n does not equal negative 1. Will we eventually be able to integrate 1 over x? Sure. But we need several tools before we get there, so we're not going to look at that in this section. For right now, our powers are going to be, well, anything but negative 1. Now, back to our examples. What if I want you to do the integral of the square root of x plus the cube root of x dx? How are you going to rewrite this problem? Same tricks as our derivatives. I can rewrite this with some fractional powers, so I'm going to get the integral of x to the 1/2 plus x to the 1/3 dx. I think I want to just keep doing this one together. Add 1 to the power and divide by the new power. 1/2 plus 1, or 1/2 plus 2/2, gives us x to the 3/2. And I'm going to divide by that 3/2. I know this is going to look bad. I'll clean it up later. I'm going to get x to the 3/2 over 3/2 plus. See what you can do with x to the 1/3. What's the integral of x to the 1/3? I'm going to add 1 to the power. I'm going to get x to the 4/3. I'll divide by 4/3. And then I'll stick a plus c at the end. Of course, this doesn't look great. We shouldn't have fractions inside fractions. So instead of saying divide by 3/2, how about I turn that into 2/3 times x to the 3/2. And the other one, let's make it 3/4 times x to the 4/3. And don't forget the plus c at the end. Next, the integral of t to the 3rd minus 2 squared dt. By the way, t is now our variable, which I can see because my differential is dt rather than dx in there. The differential also tells you what the variable is. Anything else would be a constant. I think you'd probably look at this and think like some sort of chain rule or something like that, but I haven't taught you very much about integrals so far. We don't have any sort of chain rule. We'll deal with that in section 4.5, actually, at the end of our next unit. Any idea how we can use some algebra to rewrite this so we can use the very few things we already know to be able to handle that integral? Well, what we can do is we can write this thing out twice, and we can FOIL. I can turn this into the integral of, let's see, t cubed times t cubed is t to the 6th, minus 2t to the 3rd, minus another 2t to the 3rd, plus 4 dt. I'll combine like terms and make this the integral of t to the 6th minus 4t to the 3rd plus 4 dt. I think you can finish this off. Go do your integral now. Let's see, t to the 7th over 7, or 1/7 t to the 7th, minus 4 t to the 4th over 4, plus 4t, plus a constant. I'll clean this up, and I'll make it t to the 7th over 7, minus t to the 4th, plus 4t plus a constant. I just have a few more variations to show you. Get another piece of paper out. And there's people standing at my door waving. Wonderful. I'm recording stuff. They're wondering what I'm doing. Okay, let's try the integral of x to the third minus x over the square root of x dx. The integral of x to the third minus x over the square root of x dx. I haven't taught you a quotient rule, and actually we're not going to learn a quotient rule this year. Any ideas how we could do some rewriting with this? Well, for starters, I can say the denominator is x to the 1/2. And then we can separate our fraction and use a little bit of algebra to rewrite this. I can turn this into the integral of x to the third over x to the 1/2 minus x over x to the 1/2 dx. I'm definitely still not ready to go integrate. We need to go use our laws of exponents on this. Can you take a moment, simplify what's inside the integral? Let's see, when we divide, we subtract the powers. So x to the third over x to the 1/2, that's x to the 6/2 over x to the 1/2. Subtract those, we're going to get x to the 5/2. I'm not doing any calculus yet, this is just exponent rules. Minus, okay, x to the 2/2 over x to the 1/2, subtract those. We should get x to the 5/2 minus x to the 1/2 dx. You go integrate that now. X to the 7/2 over 7/2 minus x to the 3/2 over 3/2 plus a constant. Going to do some rewriting here. We'll get 2/7 x to the 7/2 minus 2/3 x to the 3/2 plus that constant at the end. Next, the integral of the sine of x over the cosine squared of x dx. The integral of the sine of x over the cosine squared of x dx. I have no quotient rule. That's not going to help me. Even if it did, I have no chain rule, so that's not going to help me. What I'm going to do is I'm going to rewrite that denominator as cosine x times cosine x. That's sine x over cosine x times cosine x dx. That probably doesn't look so much more helpful. How about this? Couldn't I rewrite this as 1 over the cosine of x times sine x over the cosine of x dx? If you multiply these together, wouldn't you get this original problem back? Still not looking super helpful. Well, this is kind of fancy. 1 over the cosine of x, that's the secant of x. Sine x over cosine x, that's the tangent of x. This problem is really asking you to integrate the secant of x times the tangent of x. And what is the integral of the secant of x times the tangent of x? That's just secant x plus c. We know very little right now about integration, and if there's trig involved and it's not exactly one of our 6 forms, let's see if we can use some trig identities, some simple-ish trig identities like the ones I did over here, to rewrite this so it is exactly one of our forms. Next, the integral of t squared dx. Integral of t squared dx. Well, the t and the x, this is an issue. If this was the integral of t squared dt, you'd be just fine with that. But it's t squared dx. You know what, before we do this, what if I asked you to do the integral of 4 dx? I'd assume you'd be okay with that. You would just get 4x plus a constant. Anything in here that does not include the x is a constant. Therefore, this t squared, I'm going to treat that like a constant because according to my differential, the variable is x. So I'm going to get t squared x plus c. Why am I allowed to do that? Because this thing is a constant, just like 4 was a constant. What was the integral of 4 dx? 4x plus c. What's the integral of t squared dx? T squared x plus c. What if I ask you to do this? What's the integral? What's the integral of that? Anything but x is a constant. So that thing, just treat it like a constant. We'll say smiley face x plus c. Finally, any one of these problems you can check by just doing derivatives. If you take your answer, find the derivative, it should become what was inside the integral before we found the antiderivative, because derivatives and integrals, they're just inverses of each other. We're going to do a bit more work with these antiderivative rules in next week's video, but I think that's all I have for today.